This is the Financial Thought Exchange podcast, where you get a little wiser by learning from the leading thinkers in finance. I'm your host, Lotta Moberg, and our guest today is Mark Kritzman. He is a CFA charter holder and a founding partner and CEO of Windham Capital Management, LLC. He's also a founding partner of State Street Associates, and he teaches graduate finance course at MIT, Massachusetts Institute of Technology. Welcome, Mark.
Oh, thank you. It's great to be here.
Now, we want to talk about a very interesting research agenda of yours around relevance-based predictions as a transparent and adaptive alternative to machine learning. This is on the screen for those watching instead of listening. You see one of the publications, but there are numerous publications out there. I've learned out there as well as a book. So we want to talk about the research agenda and this really interesting field, really. So maybe we should start by you just giving us a sense of what is the motivation behind, where is the research kind of coming from? What's the context that people should be thinking about when they start learning about the relevance of this field?
Sure. So first, before I get started with that, let me just acknowledge that this is joint research with Megan Sasonis and David Turkington. So I just want to make sure that they're recognized. This research actually goes back a long ways to 1999. And it was, back in the day, I was doing a lot of research on asset allocation. And it was always challenged to come up with better inputs, risk inputs to optimization models, namely volatilities and correlations. And it occurred to me that it might be interesting to try to separate returns that were driven by events versus those returns that were just a manifestation of the fact that asset prices are noisy. So, I, along with a couple of co-authors at the time, we developed a formula for statistically distinguishing unusual periods from common periods. And the idea back then was to see if we estimated inputs based on these unusual returns, maybe they would be more helpful in building portfolios. And it turns out that insight that unusual returns contain more useful information is the foundation of information theory, which back then I'd never heard of. But that was something that was invented by this genius called Claude Shannon. So anyway, we went about doing that. And what we discovered, so we basically said that there are returns associated with turbulent market conditions, and those were the unusual event-driven periods, versus returns, normal returns that occurred in periods that were less eventful. And what we discovered is that returns to risky assets were much lower across the board, whether it's equities or various risk premia. Across the board, returns to risky assets were significantly lower during these periods that we judged to be turbulent based on this formula than quiet times. So one application was this would be a really good way to stress test portfolios, because losses mainly occur when markets are turbulent, not when they're quiet. And so that was very early applications. And we're going back to 1999. And the statistical measure that we came up with, and I should get most of the credit would go to Eric Jacquier, who's a professor at Boston University. At the time, he was at Boston College. And he took my idea of trying to separate unusual periods from common periods, and he ran with the math. And it turns out several years later, we found out that this exact formula was originated in 1936 by an Indian mathematician named Prasanta Mahalanobis. And he derived this formula to analyze human skulls. So it turns out that it's a very, very useful formula. So, Lotta, do you want me to carry on, or do you want to interject some other questions? I could just go on a little bit longer and tell you, the steps up to relevance, and then we can talk about what we mean by relevance. Does that sound like a good plan for you?
Yeah, I won't mind just jumping right into some of at least like an overview of the technical components, as you mentioned one already, which is how unusual is the period, and maybe we can start there in terms of is an unusual period or a usual period what you want to use is more relevant or not, and then the other two components. There's kind of three pillars in this that we should maybe lay out up front, even if it's a little bit technical, but our audience is savvy enough, I think.
Yeah. So, that's a good idea. So we should talk about this formula called the Mahalanobis distance. Mm-hmm. So it's very elegant. So here's what happened. So Mahalanobis was working with an anthropologist, and they were interested in studying mixed parentage from, the British people who lived in India and the various castes of the native population. And they collected a set of skulls from a battlefield in which the people who had died on that battlefield were members of one particular caste. And then they collected another set of skulls from a graveyard where the people in that graveyard belonged to a different caste. And so Mahalanobis set about to measure all of the kinds of dimensions that you can measure with a human skull. I guess it's probably not a good idea to go into too much detail here, but you can imagine the height, the width, how far apart the eye sockets are, things like that. So he took all of these measurements, and he came up with a formula that took into account, the variation of each dimension, and also the covariation of all of these different dimensions. And so he basically, he had these different measures of a skull, different dimensions of a skull. And so you can imagine he had a whole distribution of that, from all of these skulls. And then he took so he had, let's say there's a vector called xi, which would be the values for the dimensions of a specific skull. And then you have another vector called xt, which would be the value of the values of the dimensions for the average of a particular group of skulls. And then you'd calculate the difference in those two vectors, and you'd multiply that difference by the inverse covariance matrix. And what that does is it takes into account how these dimensions co-occur with each other. And it also standardizes everything because you're effectively dividing by variance. And then you post-multiply by the transpose of those differences, and it collapses it into a single number, such that if you just handed a skull to Mahalanobis and he set about measuring it and plugging those numbers into the formula, he can tell you whether the skull came from the graveyard or from the battlefield. So that was the origin of the Mahalanobis distance. And it's been used to diagnose diseases. I think we were the first people to apply it in finance. So we used it. So he was saying, how different is this particular skull from, a group of skulls that belong to this caste versus some other caste? And what we were saying is, how unusual is this set of returns in this given period compared to what's happened over, a long history, right? So we're both measuring unusualness. So it's a measure of distance. And we were saying, if a period is unusual based on this formula, it's turbulent. So if you think about diagnosing diseases, you can imagine that you've identified cohorts of people that have all had different diseases, right? So you have one sample that had one disease, another sample that had another disease, and you have all of these, symptoms, that you have profiles of all of those people. And then some new patient shows up with some symptoms, And you use this formula to figure out, are these symptoms closer to the people who had, disease A or disease B or disease C? So it's used that way. And it's also used to, it's been used to develop autonomous vehicles. And it's just a really handy formula. So anyway, if you fast forward to around the COVID period, I started, I've been working with Meg and Dave. They weren't involved in this original research back in 1999, but I've been working with Dave for about 20 years. And we've used this this notion of turbulence quite a bit in our research here. What we next did is we started thinking about scenario analysis, and we realized that this formula. So the big challenge with scenario analysis is, you can specify all of these different economic scenarios, and you can estimate, how stocks are going to do in this scenario, how our bonds going to do in this scenario versus some other scenario, et cetera. But to come up with, a portfolio, you need to have expected returns that reflect the relative probabilities of these different scenarios, right? And so you're going along doing things pretty, scientifically, and then at the end you have to come up with probabilities, and that to me is typically a bunch of people sitting around a conference room table, just in some casual way saying, well, I think this scenario is 20% likely and this one's 10% likely, but there's no science to it. So what we realized is that you can take the variables that define the scenarios, right, take their values at a given point in time and say, what's the Mahalanobis distance of the values of these variables today from the value of those variables that prevailed during stagflation, that prevailed during robust growth, et cetera. And therefore, thereby come up with a mathematical way of assigning probabilities to these different scenarios. And then as we continued the research, it evolved into this notion of relevance. So that's the motivation. I guess now, Lotta, if you think it makes sense, I can start talking about relevance.
Yeah,
what do
go
you
ahead.
think? So,
yeah.
So the topic here is relevance-based prediction. And I guess the important thing to note here is that this is fundamentally different from conventional prediction techniques like regression analysis and its many flavors, as well as from AI-based techniques such as machine learning algorithms. It's different from both, and it's different in ways that are very favorable. So the way to think about it is, let's first think about regression analysis. This is perhaps the most commonly used technique for forming predictions. And it was actually invented around 1795 by Carl Gauss. And he invented it to help predict the motion of planets and stars to assist navigation, sailors, and I guess also people who were crossing the lands. So it was originally predicted to assist navigation, and also back in the day to, they did a lot of consulting to gamblers as well. So anyway, so regression analysis goes back a very long way, and it's very elegant, and it has a very strong theoretical foundation. Gauss showed that linear regression analysis gives the best unbiased prediction of an outcome as long as the errors around the regression line are normally distributed. Now, that's a little stricter than necessary. It turns out that the errors just need to be elliptically distributed, but I don't think back in the day, back in 1795, people were talking about elliptical distributions. So it just means it's like a normal distribution, but it allows for non-normal kurtosis. Another way of saying it, it's a distribution by which the covariance matrix can adequately define the sample of observations. So linear regression analysis works really well if there's a linear relationship. But in many cases, I would say in most cases, there's conditionality which causes asymmetry between the predictive variables and the outcomes. And linear regression analysis does not deal with asymmetry very well. So what have people done? They have turned to machine learning algorithms, right, to deal with these complexities that linear regression analysis cannot handle. So there are all kinds of machine learning algorithms. The problem with machine learning algorithms is that,
Sorry, maybe I'll interrupt you really, really quickly here. Maybe we should make people understand more, like when we talk about the asymmetries in regression analysis, because so people know there. Let's say the data fit along a line. It might look perfectly smooth here. There might be outliers, and often we remove those. So this is a little bit different here. Obviously, we should address kind of what the difference, how we deal with the outliers. And then when you talk about asymmetries, there may be, if people know the word heteroscedasticity, there might be like the volatility, decreases over time or over the set of the data and things like that, right? Are those the kind of asymmetries that you're talking about?
Yeah, so linear regression. So there are lots of ways. If you have a nonlinear relationship, let's say it's exponential or it's logarithmic, something like that, you can do transformations to make it linear and use linear regression analysis. What I'm talking about is a situation where if a certain condition prevails, there's for example, a positive relationship between the predictive variables and the outcomes. And if another condition prevails, that relationship turns negative, right? So linear regression analysis cannot handle that. So you can imagine, if you imagine a scatter plot and you have one cloud that's faced this way and the other cloud that's faced that way, linear regression is just going to have a flat line,
right,
and just predict the average as the prediction all the time. When what you'd like to do is have a system that, when the right condition prevailed, it chose the subsample of positively sloped returns, and when the other condition prevailed, it would choose the other subsample of negatively sloped returns. So that's what I mean by asymmetry.
And, right. So any U-shaped relationship, really. This could be like if I try to correlate happiness with hamburgers for myself, it's a positive correlation up until maybe the third, and then if I have to eat the fourth, then it starts decreasing, right? And
yeah, you could. So the condition,
similar examples that we can come up with.
If you already consumed, right?
Yep.
Yeah, so that's a good example. You have a positive relationship up to a couple, and then it turns negative. So that's a fairly, easy notion of asymmetry. But when you start thinking of, when you have many predictive variables, right, then it's much more common that there's going to be some asymmetries in some of those relationships. So it's just the way I think about it is that relationships change when conditions change, and linear regression can't handle that. Machine learning can be trained to handle that. But the problem with machine learning is that you have this training sample, and you develop these parameters, like a neural network where you have all of these parameters that take into account every feature of that training sample, including all kinds of conditionalities and asymmetries. And then once your model is trained, you throw away the observations and you just retain the parameters, right? And then you make your prediction. Well, the problem is, let's say you're faced with new circumstances that are not well represented in that training sample, right? The model doesn't know that. It gives you a prediction, but you don't know if that's going to be a reliable prediction or not. You would have to rebuild the model with the new set of circumstances to come up with a reliable prediction. So that basically speaks to two limitations of machine learning. One is this opacity, right? You can't really, you get an answer, but you don't know where that answer came from. And then it's the fact that these models don't automatically adapt to new circumstances. They can only operate to the extent the training sample, as it represents whatever the circumstances are that you're currently dealing with. So what we've developed is a system called relevance-based prediction, which deals with complexities such as asymmetries that are beyond the reach of linear regression analysis, but in a way that is completely transparent. You can see precisely how each observation informs the prediction. And moreover, this approach, this relevance-based prediction approach, automatically adapts to new circumstances. It's a model-free approach. There are no parameters. So that's one big advantage, or two big advantages. One, that it's super transparent, and two, that it is adaptive. Another advantage of this system, and this is unlike any other system that I'm aware of, and it sounds almost magical, is that it tells you ahead of time whether or not your prediction is going to be any good. So if you think of, and I'll try to show you how that works. I have to say, this is pretty complicated math. And I'm not using any slides or anything. So I'm just going to appeal to the audience's intuition here. But if you think of a regression model, right, the way you would judge the quality of the predictions coming from that model would be the model's R squared, right? How good a fit is there? Well, R squared is based on an average of some good predictions and some bad predictions and some so-so predictions, right? It's just an average. It doesn't tell you necessarily very much about the quality of a specific prediction. So we have a measure which we call fit. And it tells you, it's sort of like a measure of the quality of the prediction. It's a prediction-specific analog to R squared. But let me just back up a minute. So we have to, let me say how do we define relevance? Relevance it's a precise statistical measure. It's composed of similarity and informativeness. And the way we form a prediction is we take a relevance-weighted average of past outcomes. So it's just a weighted average where the weights are relevance. So if you think about how we naturally contemplate the future, right? Let's say we're not mathematicians or scientists and we're just normal people and we think about the future. We think of past experiences that are similar to our current circumstances, and we say to ourselves, well, what happened back then? If we want to figure out what's going to happen now, we try to recall similar experiences and say, what happened during those experiences or following those experiences? So we look for observations that are similar to current circumstances. And it turns out that the ones that we recall are the unusual ones. We don't recall, everyday occurrences. We recall unusual occurrences. So relevance captures both of those concepts. It's composed of similarity and what we call informativeness, which is which is measured by unusualness. So in both of these components, similarity and informativeness, are measured as Mahalanobis distances. So the first thing we do is if we want to know how relevant an observation is, because we're going to weight that up when we form the prediction, we're going to take, we're going to weight that observation as part of our prediction. So let's say that we have these predictive variables, and there's some observation, and we have the values of those predictive variables for that observation. And we also have the value of those predictive variables for the current circumstances, right? So what we do is we calculate the Mahalanobis distance of that observation from current circumstances. So since the Mahalanobis distance is a measure of difference, and we're interested in similarity, we put a minus sign in front of it. And we also have to multiply it by 1/2, because it turns out that the average square distance of observations from each other is twice as large as the average square distance of observations from the average. So anyway, that's just a technical detail, but it's necessary for the math to work out precisely. So the first
and you should start there just to make sure that there are 3 components, right? And you're talking about the first one. So there were going to be 3 parts here, and we want to give the technical, and then we also like the intuitive. So what we're talking about now, I just want to make sure that you're not jumping to the second one already. So this is, as you say, this distance, right, is the one that when we're thinking about, say, a regression and you have an outlier, it's a very different observation. Like you're saying, like you remember things that were different. And what you're saying in your framework is we actually want to weigh them more.
Yeah,
right?
well,
it's more relevant because it's not like everybody else.
Right now, I'm just talking about similarity. So what relevance is composed of similarity, the informativeness of the observation, and the informativeness of the current circumstances. So, and an observation is more relevant to the extent it's more similar to current circumstances and more different from average circumstances. There's more information in the outliers, unless they're data errors, right? As long as they're not errors, there's more information in outliers than in common observations, right? And even if they're not ever going to recur, you can think of them as natural experiments where something really extraordinary happened, and you can see, in the predictive variable, and then you can see what was the response in what you're trying to predict. So these outliers, that's where the information is. And that comes from Claude Shannon's information theory. And I do want to talk a bit about Claude Shannon at some point. But so anyway, so relevance is this, minus 1/2 times the Mahalanobis distance of an observation from current circumstances, plus the average of the Mahalanobis distance of that observation from average, plus the Mahalanobis distance of current circumstances from average. And the reason we include the Mahalanobis distance of current circumstances is because that centers relevance on 0. So anyway, that's relevance. Now what I'm going to tell you is quite remarkable. If you take a relevance-weighted average of all of the observations to form your prediction, full sample of observations, you will get precisely the same prediction that you would get from running a linear regression equation. It converges to linear regression if it's applied across all of the observations. Now, so this equivalence is really important, because what it means is that, you can get the same answer without ever running a regression equation, which is in and of itself interesting. But what it means is that the theoretical foundation that Gauss gave us to justify linear regression applies as well to relevance. Now, here's the insight to take away from this equivalence. It turns out that linear regression analysis places as much importance on non-relevant observations as it does on relevant ones. So let me make this intuitive to you. It turns out that last evening, Dave Turkington, my colleague in this research, he and I gave a presentation at Brigham and Women's Hospital to a group of medical researchers. So, they're interested in applying and using this technique to forecast medical outcomes. So, given that we were speaking to a group of doctors, I thought this analogy might make sense to them. It might resonate with them. So, this is to explain the fact that linear regression analysis places as much importance on non-relevant observations as it does on relevant ones. It just flips the sign of how they inform the prediction. So I said to the doctors, imagine you go to your doctor, you're feeling ill, you go to your doctor examines you and then prescribes some medication. And you say to your doctor, well, what should I expect? Is this going to do the trick? Will I feel well once I take this medication? And suppose the doctor says, well, yes, we've tested this on a very large sample of other people who have the exact opposite health profile as you do. And they all got really, really sick and nearly died. So this should be good for you, right? Now that sounds pretty, you wouldn't have much confidence in that medical advice, right? But that is what linear regression analysis does. That's the logic it uses. And if the relationship truly is linear, it works. But so what that led us to recognize is that we could probably form better predictions by taking a subset of relevant observations and forming the prediction from those relevant observations and discarding those that are not relevant, that are just contributing noise or actually counteracting the information in the relevant observations. So that's what we call partial sample regression, because we're just using part of the sample. So let me just pause there and see if you're okay with this so far, because what I want to do, there are three key features. So there are three components to relevance, but there are three more overarching features to relevance-based prediction. So there's relevance, there's this notion of fit, and there's this notion of codependence. So what I wanted...
Yeah, maybe we can revisit relevance first, because even though you feel like you're looking at every corner of this, I think you did go through it fairly quickly. So there, a paper of yours looks at the prediction of performance of NBA players, their prospects, and maybe it'll be useful for us to take that as an example. If we look at, say, so this is a prospect from the NBA, completely obviously not finance. It's an illustration of how you can apply this to basically anything. And you're not an NBA expert. It's just showing like I can take any data and I can apply this. But it provides a pretty simple example. So maybe if you take the relevance and the three components of that, and what do we do in those three steps with the observation of a player versus the other players, maybe that would be helpful at this point.
I could do that, but you see, there's relevance, fit, and codependence, and it might. I'm completely flexible, but it might be better to just say, here's what fit is, and here's what codependence is, and here's how it gets applied in this MBA example, right? I'd be getting ahead of, to go
do what you're comfortable with. Go ahead.
Discussed fit and codependence. That might not be the right sequence. But
okay.
What we did in the MBA paper is we wrote this paper to predict the outcomes of draft prospects for different cohorts. We used 3 years. We left out the COVID years because the seasons were shortened or canceled. So the data wasn't good during the 19 and 20, but we had 18, 21, and 22. So the people who were being drafted those years, and what we wanted to do is predict outcomes for them in their rookie season. And we based that prediction on players who had been drafted in prior years and how they performed in their rookie season. And so the players in this case are the observations, right? And each player, we measure the relevance of each previously drafted player to the prediction for the draft prospect. And we take a weighted average of the sub sample of relevant prior players to form the prediction. And it worked really, really well. Even though we're not experts in basketball, we came up with some, I think, pretty reasonable predictive variables, and we collected all of this data, and we applied this methodology. And what we were able to show is, we tried to predict two things. One is a measure called value over replacement player. So it's a composite statistic that attempts to capture how much a player is contributing to the success of the team while the player is on the floor. So that it's value over replacement player. And for rookie players, on average, it's negative because they're just not as good as more experienced players. But what we were able to do is show that the players that we predicted would have a favorable performance based on this metric in the rookie season did have significantly above average performance based on this metric, and those that we predicted would do badly did badly. So there was really great separation. But this brings us to this second key feature of relevance-based prediction, which is fit, because fit tells us how much we should trust our prediction. And so getting back to this basketball example, so we showed that across all of the predictions we made, we were able to identify with fairly high reliability those players who did well and those players who didn't do well. But then when we took a subsample of all of our predictions and just took the predictions that with the 50% highest fit, the separation was significantly greater. So what we showed is that not only can we predict which players will do well versus which ones will do poorly, for those that we have high confidence, we can predict much more reliably the differences in performance. But let me talk about fit, because this is a really important concept. And here's the intuition of fit. Suppose that you ask two people who are experts in a field some question in that field. So they're equally expert, and they give you their answers. And let's say they both give you the same answer. Well, you would have confidence in that answer, right? Because these two equally qualified people agree. But let's suppose in another case, one gives you the opposite answer as the other. Then you wouldn't have confidence. You wouldn't know which one to believe. You wouldn't have confidence in either of their answers. So fit is basically measuring the alignment of expertise with outcomes. So the way to think about it is, what we do is we look at every pair of observations that go into a prediction, every single pair. And we say, what is the relevance of the first observation? What's the relevance of the other observation? And then what is the outcome? What are the whys? And if they both have high relevance and high outcomes, then they're aligned. If one has high relevance and a low outcome, and the other has high relevance and a low outcome, they're also aligned. But if one has high relevance and a high outcome, and the other has high relevance and a low outcome, they're not aligned. So fit measures this alignment in a precise mathematical way. Does it based on the z-scores of the relevance weights and the outcomes. And so we take a weighted average of fit across all of the prediction tasks, across all of the pairs of observations that go into a prediction task. That's what we call fit. It's a measure of alignment. You can also think of it as the squared correlation between the relevance weights and the outcomes. Now, what's really interesting about this is that if you take an informativeness weighted average of fit across all of the prediction tasks, it converges precisely to R squared. So you can think of fit as sort of and R squared for an individual prediction. So it's so much more nuanced than R squared, because it's not just giving you it's not just based on an average of some good predictions and some bad predictions. It's telling you for each individual prediction how much confidence you should have. So that's fit. The next feature that I want to mention, and then we can return to the basketball example. The next feature is this notion of codependence. So most models use, the same observations and the same predictive variables for all prediction tasks, right? What relevance does is it identifies the optimal combination of predictive variables, given a set of observations for each individual prediction task. So the way to think about this, imagine a grid where the columns are different combinations of predictive variables. So each column, you're forming a prediction on some unique combination of predictive variables. And then the rows are just thresholds for defining the relevant subsample. So the elements of this grid are just, a given set of predictive variables and a given set of observations. So if the upper left cell of this grid would be all of the predictive variables and all of the observations, that's basically equivalent to linear regression analysis. So relevance-based prediction dominates linear regression analysis because it always recovers linear regression analysis, right? You just choose the cell that has all of the variables and all of the observations, and that's linear regression. The other cells have, different combinations of variables and different subsets of observations. So the idea is, to the extent there's conditionality, there's asymmetry, those other cells are going to do better than linear regression analysis. Now, what you could do, so each cell will have a prediction, right? It's the prediction for those variables and those observations. So it has a unique prediction, and it also has a unique measure of fit. So what you could do is just search that entire grid, find the cell that has the maximum fit, and use that as your prediction. That is not a bad approach, but there's a better approach. And the better approach is to take a weighted average of all of the predictions across all of the cells, where the weights are the relative reliability of those predictions. So in this way, you're sort of diversifying your prediction across many different calibrations, that is, many different combinations of predictive variables and observations, but you're doing it in a way that bends toward those, the calibrations that have higher fit, that have higher reliability. So that's, that's this notion of codependence, that the prediction task depends. Go ahead. I'm sorry.
So this sounds a little bit like lasso regression in machine learning, right? Where we're talking about selecting for variables and having a model that just doesn't throw in all of them, like what parameters you want to use, what factors, say in finance. Is it similar to that?
It's better than that in a very important way. So you can think of lasso and ridge as selecting variables or downweighting variables or eliminating variables. But it assumes that, after it's done, it assumes that the variables that are being used it assumes that a variable is either always useful or it's never useful, right? And what we're saying is that variables are sometimes useful and sometimes not useful. It depends on which observations you're using, right? And it also, it depends on the specific prediction circumstances. So, a very obvious example in finance is inflation, right? Pre-pandemic, we hadn't had inflation, since the 80s. Nobody paid it. It was not an important variable for anybody's prediction model, right? And now it's probably the most important variable for, predicting, asset outcomes. So it tells, lasso wouldn't figure that out. right? But this does. Again, each prediction task has, the choice of the variables depends on the observations, and the choice of the observations depends on the variables, and they both depend on the specific prediction task. So each prediction task has its own customized set of variables and observations. And then when we do this grid approach, we take, we consider all of them, all different calibrations, but in a way that tilts toward the ones that are most reliable. So, and this helps to guard against data errors, right? Because let's say that you just looked at that grid and you chose, this combination of variables and observations that had the highest fit. It could be that there's a data error that's driving that, right? It's unlikely that that same error is going to contaminate all of the cells in the grid, right? So we're sort of, try to diversify a little bit to guard against data errors. So anyway, that in a nutshell, it's a very big nut, I guess, is relevance-based prediction. So relevance measures how important an observation is to a prediction. Fit measures how much confidence you should have in an individual prediction task. And codependence recognizes that the choice of the observations and the variables that you use depend on one another and on the prediction task at hand. Now, let me tell you one more thing, and then if you like, we can go back to the basketball example. It turns out that the key innovation that enabled ChatGPT and other large language models is what they refer to as attention, but it's actually relevance. So, in the vernacular of LLMs, relevance is what they call attention. And so, what are they predicting? What does a ChatGPT need to predict? Well, it's given a passage, right? It has to try to interpret what the passage is asking it to do. So all of these words in the passage have, several meanings, unconditional meanings, right? And what ChatGPT needs to do is predict what the contextualized meanings of all of the words are, and it does so, by the formula of relevance. So relevance has a covariance matrix. In ChatGPT, they have what's called a learned matrix. So the learned matrix, it performs the same function as a covariance matrix does. It connects words with each other based on semantics and their position in the passage. But it's just uncanny. It has minus 1/2 similarity measured as a Mahalanobis distance, where they have this learned matrix instead of a covariance matrix, plus the average of the informativeness of current circumstances and the informativeness of the observation. So it's the same formula, and then they take a weighted average. They do censoring, just like we do in our partial sample regression, and they take a weighted average of the retained observations, and they use exponentials when they take the weighted average, but it's isomorphically equivalent to relevance. So that's just an aside that we learned.
No, that's fascinating. Yeah, that's fascinating. Yeah, I think if we do go back to just the illustration for the relevance part, because to put the math in kind of more practical terms here, the three parts here of relevance, I think this example illustrates pretty well, right? So one is, right, when we were talking about the outliers, how that is actually important, which is when you look at a draft prospect, right, in this example, we were trying to predict if this guy is going to perform well, make it, whatever you want to say, right? How good is this guy or girl, whatever, girl, guy. One is how different, right, is the observation that you're seeing from the person that we're trying to predict the success of. And then you look at also how different both of them are from the averages of the full sample that you have. Right?
Yep.
And so let's try to help the audience a little bit, just as we're closing here, like the intuition behind this. Like the first one is how special is this information? If it's just the same information, it's less valuable, right?
Right.
And the other ones have to do with, well, are you relevant from the sample as a whole, or are you so different that we should maybe ignore you because you had other things going on? And we do that for both the ones that you're trying to predict and the person helping predict and that, meaning the data about and each player that you're using in your sample to predict this one person's success.
Right. So
is that roughly kind of how you would describe it as well?
Yeah, that's very good, Lotta. So let's say we're trying to predict, how good this player is going to be based on some metric in his rookie season. And our observations are players who were drafted before him. So we know, and we have these predictive variables, like we have physical attributes like height and weight. We have, college performance metrics, shooting average, rebounding, steals, things like that. And then we have information like, what college did they go to? What conference was that college in? And then what team were they drafted by? So, and what we see, so we form a prediction, and then we can, what's, again, the beauty of this is there's this enormous transparency. We can see which, how every single player, so we have, maybe we're predicting for 30 players and that we have good information on, and we have maybe 350 previously drafted players. We can see precisely how each of those previously drafted players is weighted in forming that prediction. And what we see is that, if we're trying to predict the performance of somebody who's going to play center, that the most relevant players tend to be very tall players who also played center, and the least relevant ones were guards. In the example of the paper, we're forecasting the outcome for a guy named Mark Williams, who went to the Charlotte Hornets, who was actually a very, very good basketball player. It turns out that one of the most relevant previously drafted players to form his prediction was somebody who went to the same school, Duke University, that he went to. So the coaching has something to do with it, right? So you get a lot of things that make sense. So we get the prediction. We have we have the values of the predictive variables for the draft prospect. We have the values of the predictive variables for all of the players who came before. We can see which players were relevant. We can also see what's the fit of all of the predictions, which ones should we have more confidence in than others. And we can also see which predictive variables were used more frequently for each player. And you get, different variables for different players. That's so different from, regression or machine learning, because everything is customized to each prediction task. Before we start, I don't know how much more you want to go on here, but I do want to talk a little.
Yeah, we should wrap up.
Can I finish by talking a little bit about Claude Shannon?
Sure. Go ahead.
And
so this is very much a very important central historical figure in forming this whole field.
Yeah, the two key people are, well, there are many, but the two key ones are Mahalanobis and Claude Shannon. Claude Shannon was the greatest genius of the 20th century, right? So you have Shannon is up here, there, and then Einstein and, say, von Neumann are tied for second, right? It turns out that von Neumann, and Shannon overlapped at the Institute for Advanced Studies at Princeton, so they knew each other, and von Neumann knew Einstein, and von Neumann said that Shannon was the smartest person he'd ever met. So this is not just my
hence proof. Yeah.
So anyway, so Shannon invented information theory. And I said, the idea there is, So basically, information theory says that information is an inverse logarithmic function of probability. Okay. And I have a really compelling way to make this point. Imagine you ask 10 people to choose a number from 1 to 10, right? And then you look at the sum. If the sum is 100, first of all, that's very unusual. The likelihood is 1 in 10 billion, but you know everything. Everybody picked 10. There's no more information to be gained. If instead the sum is 99, still very unusual, it's 1 in a billion, so it's 10 times as likely, but you lose one piece of information. You know that somebody chose 9, but you don't know who. And then as you move toward 50, what you'll see is that the probabilities change multiplicatively, but the information changes additively, right? It gets lower and lower as the probabilities get higher and higher. So that's where you have this inverse logarithmic function, which justifies our argument that outliers contain more information than common observations. So Shannon, if you Google Shannon, one thing that'll come up is he wrote the most important master's thesis in the history of the world. And what he showed it as master's thesis is that all of knowledge can be represented as sequences of ones and zeros, right? So he invented digitization as a master's student. Then he went on to get his PhD, and he went to Bell Labs, right? He went to work for the phone company. And this is in the early 40s, maybe late 30s, around that time. And, the big challenge back then was how do you transmit messages quickly and accurately across great distances? And they viewed it, the phone company viewed it as an engineering problem. We have a signal. How do we boost the signal without boosting the static in the channel, right? Shannon said, forget engineering. It's all about math. And it's all about redundancy. So most languages are about 80% redundant. And what he figured out is that if you want to increase the speed of the transmission, you reduce the redundancy, right? But the problem is that if you reduce the redundancy, it's possible that a 1 in the sequence of zeros and 1, a 1 might be received as a 0, the message gets distorted. So to increase accuracy, you have to increase redundancy because it's exponentially less likely that the same error is going to be repeated multiple times. So he figured out, based on the frequency with which these, the symbols of a communication system appear, the optimal amount of redundancy to balance speed and accuracy. So the bottom line is, you can take a picture on your cell phone and send it across the world almost instantaneously. That's all due to Claude Shannon. Those are ones and zeros bouncing off of satellites that Shannon figured out mathematically back then. So he worked for the phone company. So anyway, I'm going to show you this mug that we have. It's a mug. Oops, there you go. So the skull is from Mahalanobis, right?
Okay.
Analyzing.
And the phone is from Shannon.
Shannon. And then if you look at the other side, you have the, let's see where I put this. You get the relevance formula. So there you have.
Oh, it's too far away. We'll post it in our show notes.
Pardon me?
No, we'll post it in our show notes.
Good. Excellent.
It's hard to see. Yeah. No, that's excellent. Yeah. No, this is really fascinating. I think that it's, I really hope that our listeners and viewers here take away, one, there are linear regressions, and also anything machine learning and AI is not the be all and end all. There are other options out there, and this is a really, really interesting one, maybe the best one, I don't know, depending what you do. But really look into the research, and the papers that you have are very accessible. You do not have to know a lot of math. I don't know a lot of math, and to really understand what's going on when you see it on paper. I also really hope that our audience takes away, you started with the example of Maharobolis looking at skulls, and how this as a social science, how much you can take from other fields that are also kind of like social sciences, which is measuring complex systems, and the biology can inform, a lot, right? We have Mandelbrot sets that we're actually accepted now in finance, things like that. So keep looking out there, be a little bit cross-disciplinary, and there are fields, there are, more things to be discovered, right? In those kind of having inspiration and taking inspiration from other areas. You did not, invent the components, but you're an innovator in terms of putting it all together.
Right. Yeah. Yeah. I think that, I've been all over the world presenting this to investment professionals, and there's a lot of uptake. There's a lot of enthusiasm, especially from the data science community. So, and we're, as you pointed out, we've also applied it in sports, and we've had some really interesting conversations with professional baseball teams and basketball teams. And we're now working with a couple teams in the medical field as well. So, I think this is going to become a very widely used technique. And I think it's going to be an interesting alternative to AI-based approaches because of its transparency, right? If you think of sports, it's so transparent that the analytics professional can have a meaningful conversation with the scout who doesn't know any math at all, right? Because they can say, hey, here's the guy, the analytics guy could say, here's the player who's having the biggest weight in forming this prediction. What do you know about this player, right?
Right. No, that's excellent. So as we wrap up here, anything else that you want to say to our audience in terms of what they should look for in terms of your research? And we'll link to articles by you here. But I don't know if there's anything else we want to point to.
I could say there's a book that we wrote that you can get that goes into consent approach. I'm not trying to, the whatever royalties, they all go to charity. So it's not trying to
great.
Too salesy here, but the book goes into a lot of mathematical detail. It doesn't have the latest innovations about the grid prediction and the codependence, but it goes into a lot of detail about how it was derived.
So highly recommended. Thank you so much for joining us today, and thank you everyone for tuning into the Financial Thought Exchange podcast. If you like our content, please like this video, subscribe, all the good stuff. I've been your host, Lotta Moberg. Our guest was Mark Kritzman, and we'll see you again soon.